The name of my talk today is a funny thing happened on the way to the Phoenix. It's, other than being a bit of a shout out to a Toronto concert hall with the same name, it's really a bit of a teaser. The meat of my talk today is going to be mostly about the stuff that happens in the network underneath your Phoenix app and between your Phoenix app and your browser. The bits underneath there, I think, obviously power a ton of the magic that we all know and love about Phoenix. They also exemplify some of the most powerful patterns that OTP has to offer. So I'm really excited to talk about those. Some of you may have seen a talk that I gave at last year's Elixir Conf, where I introduced, I've spent the past 2 years of my life tinkering in the basement, writing a web server in Elixir that I call Bandit. Last year's Elixir Conf is where I introduced it to the world. That talk was very much kind of about the high level of what a web server does. Today's talk is really about how a web server does that. So it's going to be a lot more about the how than the what. The two talks are very complementary. If you find this stuff interesting, there's going to be a link to that Elixir Conf video at the end of this. Highly suggest you watch that. And I've also got some good news about Bandit today, so let's jump in. So the spiritual center of the talk today is ultimately about supervision and process models within the beam and how those are exemplified by the network stack underneath Phoenix. But to do that, be able to talk about that, we have to do some work first. So we're going to talk first a bit. This is like the worst contrast projector. Hopefully, this is the only slide with bad contrast, so I think we'll be okay. We're going to talk about what Phoenix is in the first place. We're going to talk about how Phoenix interfaces with the outside world via an API called Plug. We're going to talk about how we serve the Plug API. I'm going to give an update on Bandit, and we're going to talk about what an HTTP server does very quickly, and then we're going to talk about how the process models that the Beam provides lets us scale that web server really effectively. And then finally, we're going to put this all together and show how everything underneath Phoenix actually works the way it does. So throughout this talk, we're going to be returning to a common question, which is what's underneath Phoenix? This is going to come up again and again and again. So the first thing that we need to do to answer this question is to ask, well, what is this Phoenix thing anyway? And a really gross simplification of it might be that it's a web server, right? It serves web content that can be rendered pages, that can be a JSON response, that can be WebSockets. There's obviously a lot more going on, right? There's the Ecto stack, there's the pub sub layer, there's a bunch of other stuff, but for the purposes of our talk today, we're going to be looking specifically at the HTTP part of Phoenix. So in the HTTP stack within Phoenix, clients make requests for pages, and those requests are fundamentally isolated from each other, right? Obviously between two separate, users on two separate Chrome instances, but even within a single Chrome instance, even within a single page, the separate lines in your network inspector in Chrome at a protocol level are totally distinct from one another. They're processed totally separately, and if they both go to Phoenix, Phoenix is none the wiser that those come from the same machine. And the first point of entry of each of those into Phoenix is via the Phoenix.Endpoint behavior within Phoenix. The Phoenix documentation describes this as, quote, the boundary where all requests to your web application start. It also has a ton of upward-facing behavior that interacts with bits inside Phoenix itself, things like the controller stack, view rendering, a bunch of other things. Not going to be talking about that today. Today we're talking about what's underneath Phoenix and not about Phoenix itself. So the boundary where all of our requests to our web applications start, that's a little bit heady, but ultimately it's not as complex as you might think. Requests come into Phoenix via the Plug API. Specifically, the Phoenix.Endpoint module within the project implements the Plug behavior. Some of you may have seen the Plug API before, either writing lower level web servers or perhaps seeing it inside pipelines in Phoenix. It's the same Plug. And Phoenix.Endpoint, like I said, implements the Plug behavior. If you're curious, there's the ref for it in the project. So what is the Plug API? Well, it's an abstraction over HTTP requests and responses, which is a kind of heady way of saying that given a request, an HTTP request, it allows an application to be abstracted away that describes how to respond to that. And the general idea is that you abstract an HTTP request as a call to some configured modules, to a Plug module's call function. So in this case, this is kind of the simplest hello world version of a Plug that you can have. There's one call to this call function for every web request that comes in, be that from curl, be it from Chrome, it doesn't matter. Every one of those turns into a call to this call function, and the details of that specific request are passed in this con structure, which is an instance of the plug.con structure. These requests are passed in there, and then the implementation determines, based on that, what it wants to do. And so in this case, we render a plain text hello world back to the client with a response code of 200. As it happens, this pattern composes very well, right? So much so that Phoenix uses this internally to build pipelines and to pass things around. So this con and this call is very similar to the con and the call that you may have seen within Phoenix. This is the same con structure that gets passed around in controllers. And that essentially abstracts all the way out to the boundary where it starts talking to the outside world. Indeed, Phoenix itself is actually just a really complicated plug, right? At least this is the HTTP part of Phoenix. The awesomeness like the ecto layer and pub/sub and all of that other stuff aside, the web-facing part of Phoenix is just a very, very clever plug. Just a very, very clever plug. So this realization lets us dive a little bit deeper into the journey today, because asking what's underneath Phoenix, if it's just a plug, is really asking what's underneath plug. And given that plug is an abstraction over HTTP requests and responses, it shouldn't surprise you that what's underneath the plug is a plug-aware HTTP server. Cowboy, we've all probably seen as the go-to plug-aware HTTP server in the Elixir and Erlang worlds today. Is it actually an Erlang library? So it doesn't know anything natively about plug. It's interfaced into plug via the plug.cowboy module, which is what you've probably seen within Phoenix mixed deps files. And it kind of looks like this, right? Phoenix runs an instance of Cowboy internally within its process tree. That's hosted within Phoenix's process tree. And it looks kind of something like this. So I'm going to hopefully be able to speak into the mic. So I've got a very standard Phoenix application here. This is just a standard, there's a few very small changes to it. You'll see those in a moment. I run a server here and go over to my browser and I go to localhost. I go to localhost 1000 and I mistype it and oh, lovely. Bueno. Localhost 4000. Oh, there we go. Whew, okay. And we see the standard Phoenix application, that Hello World page that we expect to see. If we go back to our terminal, we can see that this is hosted out of the page controller at the very top here. So we're going to go really quickly into page controller. And instead of rendering a response here, we're just going to raise an exception. And we're going to do this so that when we start our server and we go back to our web page here and we reload, we now see a stack trace that shows us exactly where we are within context here. And you'll see the interesting bits here. There's some frames at the very top from our application. There's some Phoenix frames, and at the bottom you'll see some Cowboy frames. Hopefully, let me embiggen this so you guys can see it. There. So Cowboy sits underneath Phoenix, as we just said. So you might be wondering at this point why I'm spending all of this time, having just written a web server for the past 2 years of my life, why I'm spending all of this time talking about Cowboy. And I mention it largely just to contextualize things, but also because up until today, Cowboy was the only game in town to be able to run Phoenix. I'm proud to say that after a lot of work, that's no longer the case. Bandit now runs Phoenix. This is, with a few caveats, we'll get to them. So this is the first time that I'm aware of that we've ever been able to have an entirely 100% Elixir stack from top to bottom underneath Phoenix, which I think is pretty cool. If you haven't seen Bandit before, it is a plug native HTTP server. Serving plugs is literally all it does. Its byline is an HTTP server for plug applications, written primarily by your faithful correspondent. And here's the quick sell sheet for it. It's plug native, written 100% in Elixir. Really robust HTTP compliance. We run external third-party automated validation suites in CI, so pretty confident in its conformance. Written from the ground up to be correct, to be fast, and to be easy to understand, both partly from being written in Elixir and also just the way that we've written it has been really focused on demystifying network code for people. Really fast. I talk about this in my ElixirConf talk, about up to 5 times faster than Cowboy in some scenarios, so that's kind of nice to have. And as of 0.5, which comes out today, now supports HTTPS Phoenix apps. So we still don't do WebSockets, but anything that uses Phoenix as an API server that just does JSON back and forth, or anything that's just HTTP, we fully support that. It's a one-line change to enable it in Phoenix, and the work is entirely contained within the Bandit project, so you don't have to fork Phoenix, you don't have to update Phoenix, you can even do this on older versions of Phoenix as well. And this really sets the stage for us to be able to start building WebSocket work, which I'm really excited to be able to land very soon. So let's see what that integration looks like. So we're going to go back to our live demo here, and I'm going to make 2 changes, one of which I've already made. And the first is go into our mix.css file And if I scroll all the way down, for some reason my scrolling is not working today because I'm probably there. There we go. Okay. I have added already this Bandit dependency, and I did it before just because I wasn't sure what the network was going to be like here. So I've already loaded Bandit in as a dependency. I'm going to go into our config.exs file, and I'm going to add to the config stanza that configures our endpoint, I'm going to add the one, what the heck just happened? And lovely, do not, okay, I'm just going to type it by hand. Adapter, Bandit, dot. Don't ever let anybody tell you that coding over your shoulder is not tedious. Okay, adapter, bandit.phoenix adapter. And now, when we start Phoenix, you can see that it's now serving Phoenix off of Bandit. And if we go back to our stack frames here and we reload, everything at the top is exactly unchanged, right? We have the standard application stack that we had before that ends in the endpoint, being the interface of Phoenix into the outside world. Everything underneath that now is Bandit. And you'll notice that everything underneath there, up until the standard library beam stuff, is also Elixir. So I think that's pretty cool, right? This is the first time that I'm aware of that we've ever shown Phoenix running on anything other than Cowboy, and we've ever shown it running on a fully Elixir stack. So Bandit 0.5 drops today. If you want to see details about how to do this, you can check the GitHub repo out. Really hoping that this is going to accelerate Bandit's adoption now that people can actually use it for useful things in Phoenix. So anyway, enough, thanks. Enough self-aggrandizement. Let's get back to the task at hand, right? Namely, asking the question, what's underneath Phoenix? So we're here today to answer this, but we've already discovered that this is equivalent to asking what's underneath plug. And we've already discovered that what's underneath plug is a plug-aware HTTP server, or in the case of Bandit, a plug-native HTTP server. So what does an HTTP server do exactly? At least from a process perspective. Let's talk about that for a bit. So I'm going to be talking for the remainder of this talk about how Bandit deals with HTTP internally. Bandit was very heavily inspired by Cowboy, so the process models are very similar. Most of what I say maps more or less directly onto Cowboy, but I will be speaking about Bandit specifically for the rest of the talk. So a web server has a pretty simple job when you break it down. Number one, it listens for connections from clients, and then it handles each of those connections separately. I want you to focus on the word separately here. This is going to come, this is a load bearing separately. You'll see this come up frequently throughout the rest of the talk. So each of these handling each of these connections looks something like this. You'll parse, let's say, the HTTP request into a plug.const structure so that we can describe what the request looks like. We'll pass that structure to a plug implementation by calling the plug.call function on it. And we'll provide some backing support for that implementation to be able to do things like send response headers, write a body out, do whatever it needs to do with the request. So this problem naturally splits into two parts. The first of those, listing for connections, is generic, right? This is common across any at least any socket-based, any TCP protocol. They're all going to listen for requests in the same way. Where they differ is how you handle each of those connections once they arrive. So this is where the specifics of something like HTTP come up, or FTP, or Gopher, or whatever you wanted to write. So if we wanted to factor out the HTTP specific parts of this to keep the generic parts generic, we might end up with something like this, right? We have some generic parts that's essentially a loop. In this case, it'll loop around, wait for a connection from a client. When a connection comes in, we'll pass it through that HTTP pipeline. But we can go a bit further with this, and we can do something that looks like this, where our generic part basically just calls out to a module. You can imagine how you would be able to configure this module. And then the module itself is where you implement, so let's say HTTP or Gopher or whatever you'd have. And it turns out that this partition between the protocol-specific parts and the generic parts is really the correct abstraction here. So much so that these two parts are actually handled by separate libraries within our stack. Thousand Island, so Bandit is the HTTP server that I spoke about before. It implements the protocol-specific aspects of this. So it's handed a connection that already exists, that's already been made from a client, and it processes that connection and runs an HTTP conversation with the connected client. Thousand Island is an implementation that sits below that. It's what's known as a socket server. Its job is to handle the generic parts of accepting connections. So basically, it loops around and waits for connections. When it receives those, it hands each connection separately up to a library such as Bandit to process it, depending on what the protocol at hand is. And so if we take this and we combine this with what we've already learned, which is that Bandit serves Phoenix, right? We see that this forms something that looks a lot like a classic protocol stack diagram. We have our application layer on top that sits on top of a protocol layer, in this case, that's running HTTP, and that protocol layer sits on top of a transport layer, in this case, running on TCP or SSL or what have you. So we've talked a little bit about Phoenix and Bandit. Let's talk about Thousand Island now. Thousand Island is a socket server, but what exactly does a socket server do? Well, it listens for connections over TCP or TLS. TLS is the fancy name for SSL. And it hands them off to an upper protocol layer, such as an HTTP server, as Bandit. It provides underlying functionality to be able to send and receive bytes to the connected client. It handles some underlying transport concerns that are generic. Doing certificate negotiation is a good example in the case of SSL. And it does all of this, most importantly, it does all of this in a way that's efficient and scalable and lets the higher level libraries not have to worry about performance so much in the large. So in the case of Thousand Island, here's the sell sheet for Thousand Island. It's a nice little library that implements that pretty well. Written 100% in Elixir, supports TCP, TLS, and Unix domain sockets, fully wired for telemetry, including the ability to be able to trace individual socket connections and see bytes coming and going on the wire. If anybody here has written low-level stuff or ever had to worry about what's happening on the wire, this is incredibly useful. Very scalable, easy to understand. There's only about 1,700 lines of code in the entire project. Again, written with the primary purpose of demystifying this code for developers, so it's purposely written to be approachable. And it's got a very powerful behavior to allow higher level protocols such as Bandit to be implemented on top of it. We're going to take a quick look at what those look like right now. So between Phoenix and Bandit, we know that Bandit serves Phoenix by way of the plug API. That's the abstraction that sits between those layers. The abstraction that sits between Bandit and Thousand Island is what we're going to talk about now. This is codified in the Thousand Island.handler behavior. And this formalizes how higher level protocols get to sit on top of Thousand Island. So the TLDR for this is that you can think of it kind of like a gen server for sockets, right? It's got an API that looks and acts an awful lot like gen server, like the gen server API. And it looks something like this. This is the core of the Thousand Island.handler behavior. There's about a half dozen functions in total. Handle connection and handle data are the two most important ones. Handle connection is called by Thousand Island when a connection is made from a client before any data has been sent to the server, and it passes in the socket as well as a state that you yield back in the manner like a gen server. So this is useful when you want to do something as soon as the client connects. Otherwise, we also have this handle data callback that's called by Thousand Island whenever the client sends data unsolicited to the server, and it passes the data as well as the socket. In both of these cases, they return a tuple that looks like close in a state or continue in a state. The state part is the same as the state in a gen server. Close and continue tell Thousand Island whether to close the connection at that point or keep it open and continue waiting for more data. So let's look at some examples. So this is a marvelous little piece of internet history here, the daytime protocol. So the protocol says that when a client connects, the server sends it the date in some arbitrary format and then closes the connection. So we can implement that in Thousand Island. This is the complete implementation of that protocol. This would scale. You could handle hundreds of thousands of people asking for the current time with 10 lines of code. When a connection comes in, we build the current time into a string, and we use the Thousand Island.socket function to send that string, just that ASCII string, out to the client, and then we return close to close the connection. Another old gem here is the echo protocol. This one says that the server should stay silent and only return data back to the client when the client sends it data. So if the client sends ABC, the server echoes ABC right back to the client and continues doing that until the client closes the connection. So we can implement that here, perhaps unsurprisingly, by overriding the handle data function, and then the data that's passed into us, we immediately turn it right back around and send it to the server, again via Thousand Island.socket.send, and we return continue to tell Thousand Island to keep the socket open. So both of these this is really the entirety of how higher level libraries talk to Thousand Island. And so you could imagine that Bandit's implementation might look something like this, right? We would take when a client connects, we call this fictional bandit.doHTTP function that doesn't actually exist. And it goes and runs an HTTP conversation on that socket. And when it's done, we just close it off because presumably we're done. This is a gross simplification, of course, right? This doesn't account for keep alives, HTTP keep alives. It doesn't account for HTTP2's structure. But at a basic level, this is fit for purpose. And Bandit, in fact, looked very much like this in its earliest days. So I mentioned earlier that thousand-island.handler is basically a gen server for sockets, and that kind of looks like, you can see how it's got the handle functions that take and receive a state and some other data. And this is actually more than skin deep. In point of fact, thousand-island handler processes are actually gen servers under the hood. Every distinct client connection that comes in runs in its own process within its own gen server. And so this means that you can do really all the normal useful gen server things with a client connection. You can register that process that's running that in a registry in gproc. You can message between them very, very easily. You can build like a peer-to-peer messaging protocol on top of Thousand Island in like a dozen lines of code. And it's a really, really well-fitted abstraction. But it also has some implications about where your Phoenix requests run, right? Recall that Bandit is a Thousand Island handler. Bandit now runs Phoenix. So each Phoenix request actually runs inside of its own gen server, at least on Bandit and at least with HTTP1. Your Phoenix requests, if you go and look at that stack trace we saw earlier, you'll actually see gen server frames at the very bottom of that. The case with HTTP2 is quite a bit more complicated. If you're interested in that, the Bandit README has a whole section on process models there. They're actually a kind of a neat study in how to intentionally not supervise processes. So if you're keen, for very good reasons, if you're keen to go deeper on that, that's a really good place to start for looking at sort of more advanced process models. So it's cool that we now know that each of our Phoenix connections runs in its own gen server. But what exactly, what exactly, let me find my cursor here, hold on. What exactly, my cursor's gone, great. Oh, there it is, okay. So it's cool that each connection runs in its own gen server, but how exactly do we get to those processes, right? It's cool that we can have 10,000 concurrent connections, each running in a gen server, right? And so you can sort of start to understand, given the fact that the Beam can run tens of thousands of processes, how you can have a bunch of clients all running at the same time and they don't impact each other. But how do we get there, right? How do we start those processes and how do we supervise those processes? How do they fit into a larger process tree? And to answer that, we're gonna take a step back from Bandit and we're gonna turn our attention down the stack again to Thousand Island. And we're gonna look at how Thousand Island really helps to power that. And we're gonna do that by kind of looking at the simplest possible thing that we can do that can serve a client connection and meaningfully return data to it. And it might look something like this. So in this case, this is really illustrate. I put the slide up just to illustrate what the functions are that we interact with. We first listen on a port. In this case, listen on port 4000. We get back what's called a listener socket from that. This is now telling us that listener socket represents the fact that clients are able to connect to port 4000, but no client has connected just yet. We then call gentcp.accept, which will block until a client does connect on port 4000, and it will return a connection socket that represents the connection to that particular client right there. In this case, we would have this fictional handler function that goes off and does that implements the Thousand Island handler behavior we saw before. We have everything to do that because we have the client connection, right? And then we'll close the connection when we're done. So this is kind of the simplest thing that can meaningfully send data back, but it's not very useful and it has a really big problem, and that's the fact that it only runs once, right? This will accept a single client connection, process it, and then just die and go off. So we obviously need to fix that, so let's do something like throw a loop around it. So in this case, we have the same functions as before. We're just throwing a tail recursing loop around it that has this accept function that essentially handles the next connection that comes in on that listener socket. And it's the exact same code otherwise. But there's a problem with this as well, which is the fact that it only runs one connection at a time, right? If you have a client that comes in and he's connected for multiple minutes at a time, no other clients are able to connect, right? Because there's only a single process that's running this. So that obviously doesn't jive with our ability to do tens of thousands of things at a time. So let's maybe handle this by spinning the actual handling work out into, let's say, a task. Right? So in this case, we get a connection from a client. We take that socket that represents the connection to that particular client, and we hand it off to it. We just run it in a task. We call task.startLink, and we go and handle the connection there. And so this is cool, right? Because now we're able to process multiple connections while we still have other client connections running. And it's really hard to overstate how awesome this is, right? Coming at this from other systems languages, we could easily run tens of thousands of concurrent connections here, each in their own process, and it's like 13 lines of code, right? The level of scalability that provides for the amount of effort we've expended is really exceptional. But there's a problem here as well, and that's supervision, right? So long as things never crashed here, this would be fine. But if any client connection ever crashes, it's not only going to bring itself down, it's also going to bring the server itself down and every other thing down because the processes themselves are linked via the start link. And so we solve this in probably an unsurprising way, which is to add supervision to it. Similar model here. It's like instead of explicitly, imperatively building out our tasks, we build a child spec that defines that we want this handler module to call something based on this connection socket. And we go and run that in a dynamic supervisor. And so this is starting to look like something we could get behind, right? We've got all the bases covered here, it seems at least. And graphically, it looks kind of something like this. Right, the code that we saw on the previous slide runs inside this acceptor process on the right-hand side. And when it wants to create a task, when it wants to create a process for a handler, for a connection that comes in, it talks to this dynamic supervisor process to go and actually host the connection. And a typical lifecycle might look something like this. The acceptor receives a task, or receives a connection. It goes and creates a process for client A underneath that dynamic supervisor. Then we get a second client connection in from a different client. Maybe that one's very fast running. They terminate very quickly. That process has come and gone, and client A has no idea. They've never seen it. They're in complete ignorance of it, which is as things should be, because recall, each of these processes is handled separately. Eventually, client A finishes, and we're here. So this is cool, and it works pretty well, but there's another problem with this, which is the fact that there's no easy way for the acceptor to reach the dynamic supervisor, except perhaps by using maybe a named process or something. But we can solve that in a bit more of a general way by supervising these two together and using the supervisor model to be able to model the dependencies between these two processes properly. And that might look something like this. So we start the dynamic supervisor first in our specification within the supervisor. And we only start the acceptor process once the dynamic supervisor is up and running. So this does two things. Number one is it means that the acceptor can then go and learn about the dynamic supervisor's process ID just by going and interrogating its parent supervisor to find out where it is. But more importantly, it also models dependencies, right? It means that we're not in a situation where we might have an acceptor process running, but not the dynamic supervisor that it needs to be able to host new processes. So we're not going to be in the situation where we get client connections in, we accept them, and then we're like, oh, shoot, I don't have anywhere to go and run this, right? The dependencies between these are modeled. So let's go and look at some observations from this, right? Because it turns out that this tree is really, really, really useful for being able to understand some of the subtleties of supervision and specifically the differences between supervisors and dynamic supervisors. So looking at dynamic supervisors first, hopefully the people over here can see this one. They're best used when the children that we create are on demand and they're independent. So remember what we said earlier, that HTTP connections are processed totally separate from one another? This turns out to be a really great fit for dynamic supervision because each of those client connections is hosted inside a dynamic supervisor and runs totally independent of all the other ones, which is the exact same as the semantics that we want from HTTP. They work really well when they're paired with a creator task, something that can go and create processes within them instead of having to worry about how they start things up. This kind of matches that on-demand line in the first point. And they actually are not capable of managing dependencies between their children, right? The whole point of dynamic supervisors is that they manage their children in complete isolation from each other. In contrast, supervisors are all about managing the dependencies between their child processes. That's what they do best. And so they work best when you have a set of supervised processes that you know about up front. And you're able to define what those dependencies are between them. And you do this by, first off, things like start order, determining, like we saw earlier, making sure that you have a dynamic supervisor started before you start your acceptor. You also can use things like supervision strategies to determine what happens when one of these things crashes, how do we go and start the rest of them. It's also kind of important to note that supervisors are best when you keep your application logic out of them. Keep them focused on modeling dependencies between their children and not on modeling aspects of your particular application themselves. They do their best job when they're able to just do their only job, which is typically the case of most processes. So now that we've looked at supervisors, I'm just going to take a quick moment here and look at this acceptor process. It's common to think that most worker processes, like workers being things that aren't supervisors, are usually gen servers. And that's often but not always the case, right? Gen servers are a marvelous abstraction, but they're not the only game in town. And in fact, the acceptor task is implemented as a capital T task. It's a very useful alternative to gen servers that I think is very often overlooked. People classically think of, and for example, in Brooklyn's talk this morning, you use them in a very kind of async await, almost ephemeral, afterthought kind of way about just being able to use them for parallelizing. They are first-class processes like anything else. You can have a permanent restart strategy on them, and they will have the same life cycle and the same restart semantics that a gen server does, for example. They don't have a permanent restart strategy by default, but it's a fully supported thing within the module. The key question that I ask myself when I'm determining whether or not I use a task or a gen server is there any other actor in my system that's going to have to be able to talk to that process? And if the answer to that is no, if the answer is I just want to have a process that goes and does its thing and does it mostly in isolation, perhaps goes out to other modules but doesn't have other modules coming back to it, it's often a really good idea to use a task. It's a much simpler abstraction, it's much easier to reason about, and it's just frankly easier to work with in a lot of cases. So having taken a couple of side trips here on observations, let's get back to where we were, right? This is where we last saw what our socket server would look like. And we could stop here and we'd get 90% of the benefit of the beam and nobody would judge us, right? We would be miles ahead of anything you could build anywhere else and we'd be fine, right? Nobody would hold us to account for this. And indeed, Thousand Island looked an awful lot like this at one point in time. But if we really want to unlock this, we can go one step further. And that's the fact that you'll notice that in this loop, even though we do the majority of our client handling inside this dynamic supervisor child task, we still have to turn this loop. We still have to start up that dynamic supervisor process, build the child spec, turn around the loop and come back. So for a short window of time after we accept every client connection, we're unable to accept new client connections until we get back to the top of the loop and call this accept function again. So we can solve this in a pretty easy way, and that's just by doing the same thing multiple times, right? Just running multiple versions of that acceptor tree. And this allows each of them to take as long as they'd like to be able to loop around and receive their next connection because there's a whole fleet of acceptors. 5? Really? I'm at 32 on my counter. Okay. All right. I'll speed it up a bit. Okay, so this is cool, right? We're almost there. We've got one quick thing to land here, and that's just a little bit of on top to be able to remember that listen task at the very beginning was a thing that we only did once for the lifecycle of a server. So we end up with a tree that looks kind of something like this. We have some stuff at the top to start things and some stuff at the top to shut things down cleanly. But generally speaking, this is actually what Thousand Island looks like today. This tree is exactly what you get when you start a Thousand Island server. The process ID that you get back from a Thousand Island.startLink call is the process ID of that top supervisor here. And that's it. That's all there is to it. So let's take a quick little look at some of the details. Emphasis on quick. First off, the rationale behind having multiple of these trees at the bottom. In Thousand Island, the number of these trees is configurable via the num acceptors parameter. It defaults to 10. I can only fit 5 on the slide, but in a default Thousand Island server, there's 10 of them. Each of them is isolated. And that has one primary benefit of minimizing the blast radius of a crash, as we'll see in a moment, minimizing the number of people that even see or care about a crash. It also helps reduce contention for resources. We don't have to have multiple acceptors competing to try to start processes underneath the same supervisor. The other thing that I want to observe here is that you want to prefer composition. You want to have lots of simple supervisors, each doing a very simple, understandable thing, versus trying to have one supervisor to kind of rule the world. This composition, it really underlies the point that supervisors themselves are just processes. And so having supervisors that supervise supervisors is not only fine, but it's actually a blessed pattern that's really common in OTP. The third thing is to prefer to expose process trees. And what I mean by that is this whole notion that we have internally here of having things that compose with each other all the way up this tree. You want to actually do that when users use your library. So in the case of Thousand Island, we don't go and run a thing inside our own application. We give you back a process ID that we expect you to wire into your application's process tree. This allows users to be able to express dependencies to and from Thousand Island as the same way they model dependencies internally within their application. So this is exactly how Phoenix does it, for example. It's also more flexible. It means that we can do things like run multiple Thousand Island instances within the same Beam instance, serving different servers on different ports, and that's totally fine. It just falls out of the model. So the last thing I want to talk about is how supervisors are kind of like restart machines, right? How they allow you to contain the blast radius of crashes. And we're going to do this by looking at some examples. So imagine that we've had this process, this Thousand Island process tree running for a while, and we have, let's say, 4 client connections. So these are 4 currently connected clients. Let's say, unfortunately, this one here crashes. So what's going to happen is his dynamic supervisor is going to be notified of that because those processes are linked. It's going to look at the restart strategy for this. And in the case of Thousand Island, we do a temporary restart strategy because we can't meaningfully restart a connection with a client. And so simply that process will die. The key thing to note here is that nobody else noticed or cared, right? All the other client connections continue to run, all the other acceptors continue to run, nobody else noticed or cared. Imagine that, for example, this acceptor process crashes. In this case, again, their supervisor is going to wake up and be notified of this. They're going to look at the restart strategy, which in this case is going to be permanent because we want to keep that process running if it crashes. They'll restart that process, we'll be left with this process tree. The cool thing here is that nobody else crashed. Even the processes, like that one handler at the bottom, which was a handler process that was created by the original handler that crashed, doesn't know or care. He continues to run in complete ignorance of the fact that the process that started that has come and gone. This example is a bit more synthetic. Imagine, for example, if this dynamic supervisor crashes. This generally doesn't happen. Dynamic supervisor is a built-in module that's essentially bug-free, but it's a good illustration, and it's something that you do need to consider if you're completionist about this. In this case, unfortunately, the child processes will die. The parent supervisor will be notified. It will, because of the restart strategies this is where you'll have the rest for one restart strategy, it will kill all of its children, restart them all, and you'll be left with a process tree that looks the exact same. Finally, a very similar approach, if this parent supervisor dies, the key thing to note here is that the whole the whole process tree underneath that disappears. When that supervisor is restarted, its responsibility is to create its children. And again, you'll be left with the same process tree you had when you started. The takeaway here is that you can't let it crash without also knowing how to restart it, right? Like we say let it crash as if that solves all of our problems. It really just creates new ones, right? And the way that you solve those new problems is to think very deeply and carefully about how you actually go about restarting your process trees when they do crash, right? These are 2 sides to the same coin. So let's put all of this together. We're nearly at the end of the talk. Let's try to string together what we've just learned. Right? We were here today to learn what's underneath Phoenix. So the answer to that is a little bit long-winded. Jesus, you can hardly see that. Contrast, not great. Okay, Phoenix exposes itself to the rest of the world as a plug via the plug.endpoint behavior module. That's served inside an HTTP server such as Bandit. Bandit runs on top of Thousand Island by implementing Thousand Island handler behavior. Thousand Island hosts those handlers inside a gen server that's fresh for each process that comes in, a fresh process for each client connection that comes in. Those connections are created by an acceptor task, which is managed inside a supervisor tree, of which there's multiple copies so that we can, accept client requests in parallel. All of this is managed by, a multi-level process tree that's rooted at a process ID that is what you get back from thousandisland.startlink. And thousandisland.startlink is called by Phoenix when it starts up, and it gets wired into Phoenix's internal process tree. So what's underneath Phoenix? A little bit of magic, not too much, just a little bit. Some surprises, not that many. Mostly things that we've seen before, right? Supervisors, gen servers, some tasks, some restart strategies, nothing super esoteric. There's no real mystery here. A little bit of careful fault containment, but very idiomatic fault containment, right? This is nothing that isn't in any of the standard library Elixir docs. Really, it's kind of a textbook example of OTP. And frankly, this is, if you're going to take one thing away from this talk, it's to not be scared of this stuff, right? People think of network stacks as being this, terrifying giant that lives in the hillsides that, is full of mystery, and it's not. It's just the same stuff that we've seen before. That's the end of my talk today. If you're keen, thanks. If you're keen to take Bandit for a spin with your HTTP-only Phoenix app, take a look at the repo linked here. I changed the color of that so you could hopefully see it on the slide, like last minute. Thousand Island, if you're keen to look at process models, is a good repo to do for that. The README is should be a pretty good jumping off point. If you are keen to see these slides or the Elixir Conf talk video that I mentioned previously, there's links to it in my talks repo. And if you'd like to get in touch, details are here. Of course, I'll be at the after party as well. Thanks again to the MPEX crew for putting this on, and thanks for everybody for having me today. It's been great.